today because many labs are moving, including my own. The topic of today's lecture is we will continue discussing the Hopfield model. So we ended the class on Sunday by discussing the problem, or one issue with the Hopfield model. Do you remember what it was? So, as Musa said, the capacity of the original Hopfield model is on the order n, or maybe n over log n, depending on how exactly we define memory capacity. But this is only true when the probability of a neuron being active in a memory is 0.5. If this probability changes even by a little, let's say to 0.55, then the number of memory patterns that can be stored, or the capacity, goes down to being order 1. So this is a major requirement of fine-tuning. So the question is, how can we overcome it? So why did the capacity go down? What was the reason? So in the original Hopfield model, what's the source of, what's the limitation? What limits the number of memory patterns? Let me write down the equation. Jij is equal to 1 over n, sum over mu, pi mu, pj mu. This is a connectivity matrix. Sorry? Well, true that the larger the number of neurons is, the larger is the capacity. This is true in the original Hopfield model. This is no longer true in the case where the memory patterns are no longer plus and minus 1 with a probability 0.5. Sorry? What do you mean the mu? What do you mean by...
When it was probability at 0.5, we got a distribution Gaussian with the lead theorem, right? I didn't understand then why when it's not true, we don't have this anymore, but of course depended on the fact that it was mixed.
Okay, so let's continuing what you said. So the way that we can think about this Jij is the following. We can say that this Jij is equal to 1 over n pi1 pj1 plus sum over mu from 2 to p pi mu pj mu. This is always j I not equal to j. Okay, so this is, we can dissociate or separate Jij to two terms. One is term corresponding to memory pattern number 1, and one that corresponds to all other memory patterns. And I just chose one without a loss of generality. Now, if we consider the input to neuron I, this input is equal to sum over all neurons in the network Jij Rj, where Rj will be the activity of the jth neuron. So the way that we thought about this problem was the following. We said, let's see whether a memory pattern is a fixed point of the dynamics. And the way to test it was to replace Rj to replace the activity of all neurons in the network with one of the memory patterns, pattern number 1, and to ask whether the input to neuron I in the network has the correct sign, that is a sign that is congruent with the desired activity in this particular memory pattern. Now, when writing it this way, when separating the Jij into two terms, we can separate the input to the neuron. We can separate it into two terms. One is a term that results from this part of the Jij, and the other one is the input that results from this part of the Jij. Now, in all the problems, including the case of unbalanced memory patterns, this is okay. This will result in input that has the correct sign. Now, what about this term? In the case where the memory patterns are plus and minus 1 with a probability 0.5, the problem was that this was a stochastic variable, where the stochasticity is the stochasticity of realization of different memory patterns in the network. And if the variance of this term is too large, then we have a problem, because it could be that this term will dominate, and as a result, the sign of Hi will be different from the desired sign. Now, in the case in the case where Pi, where the memory patterns are not plus minus 1 with probability 0.5, but with a different probability, this term, it is missing 1 over n, the contribution of this term to the input has a non-zero mean. So if all, let's say that this non-zero mean is plus 1, or is positive. So if this non-zero mean is positive, then the input to all neurons will be positive. And then the memory pattern will not be a fixed point. So in the first case, the problem was the variance. In the second case, the problem was the mean. And it is sufficient that the contribution of this term is larger than the contribution of this term, then the memory pattern is no longer a fixed point. So this is why the mean was a problem. So the question, one question that we could ask is, how can we fix this plasticity rule to overcome this problem? So remember, we talked about the case of Jennifer Aniston and all these examples, and we saw that memories are rather sparse, at least in these examples in the brain. When people model memory, real memories, they use typically something like 10%. So the idea that for each memory pattern, let's say 10% of the neurons are active and 90% are inactive. I don't think that this number 10% is really based on any concrete biological evidence, but clearly it's not 50%, and clearly it's not 10 to the minus 5. So it should be, if it's 20% or 1%, we can argue about it, or even 0.5%, but it will definitely not be exactly 50%. So how can we fix this rule to account for unbalanced memories? So to solve a problem, we first need to understand it. So why did we have a problem? Why do we have a problem in this case? So the problem is the mean, right? The problem is that this term contributes to this, to the input to the neuron, contributes a number that is either positive or negative, depending on the sparseness, and so in order to solve it, what we need is that this term will have well, that the contribution of this term will have a zero mean. So how can we change the plasticity rule such that this term will have a zero mean? Okay, good. So if we know the sparseness of the memories or the probability that the memory is +1, then we know the mean. Well, we know the mean of what? We know the mean of anything that we want that relates to the different p's. So, for example, if pi and pj are equal to 1 and -1 is the probability 1/2, the pi and the pj each have a zero mean. And the product also has a zero mean, they are uncorrelated. So how should we change this rule such that how should we change this rule so that this will have a zero mean? So we can just subtract the expected mean. So this is called the covariance rule. In this case, Jij will be equal to 1 over n, sum over mu of pi mu minus the average of p, pj mu minus the average. So in this course, this notation denotes the average over the memory pattern, average over realization of memory patterns. And if pi mu is equal to plus and minus 1 with a probability 1/2, then this term is equal to 0. And we revert to the original Hopfield model. But if pi and pj are equal to 1 and minus 1 with a different probability, then this term will not be equal to 0, but the average of this would be equal to 0. So this is a way of overcoming the problem in the Hopfield model. It's known as the covariance rule, and one can prove that with this rule the capacity goes back to the original capacity, approximately the original capacity. And to show you, to prove it to you, I'm going now to consider a variant of the Hopfield model in which neurons are not plus and minus 1 with a probability 1/2, but are equal to 1 and 0 with some probability. So in the original Hopfield model, neurons are either +1 or -1. Now we will consider a model in which neurons are either 1 or 0. That is perhaps more to the liking of perhaps more relevant or more that is biologically more plausible. Okay, questions? So let's do it. So in our new model, pi mu will be equal to 1 or 0 with probability f or 1 minus f. And as before, we assume that the different neurons and different memory patterns are independent. and the connectivity Jij is equal to 1 over n, sum over mu, pi mu minus f, pj mu minus f. So we incorporate this idea of covariance. Now we need a rule, or we need an activation function. I just said that neurons are 0 or 1. I didn't tell you what the activation function is. So our activation function is the following. We say that activity of neuron I is equal to half of 1 plus sine hi minus t, where hi is the input to the neuron, as before, sum over j of jij rj, and t is a threshold that we will discuss later. Okay, so it's a model that is similar but not identical to the original Hopfield model. Our neurons now are not minus 1 and 1, they are equal to 0 or 1, and this is the activation function. And now I would like to compute the capacity, the memory capacity in this model. How should I do it? How am I going to compute the capacity? Well, you're right that we need the dynamics. If we want to write the dynamic equation, then the equation would be something like the following: Ri dot is equal to minus Ri plus G of Hi minus T, where G of X is equal to 1/2 1 plus sine of Hi minus T. So this would be writing it in dynamically. If we write it this way, this is just corresponding to the fixed point equation. So you're right that it would make more sense to start by writing this dynamical equation and then say, okay, this is a fixed point. So what are we interested in when talking about the fixed point? Sorry? Stability. Well, before stability, we need to find a fixed point. When computing the capacity previously, we ignored the issue of stability. We will talk about stability later today. But first we need to find, what do we need to do regarding the fixed point? Plugging. What is it exactly that we're looking for? In the previous case, when we talked about the Hopfield model, it's not that we took this set of equations. We have n such equations, and we found a way of identifying all the fixed points. We did something that is simpler. We asked a different question. So this is, yeah. before that? What is it that we're looking for? I mean, naively we would say, okay, let's find all the fixed points. But this is not what we did because it's complicated. We don't know how to do it. We have n nonlinear equations. We cannot find all the fixed points. We use one memory pattern. So what exactly did we do? We plugged in one memory pattern and we asked, is this a fixed point? We didn't ask anything about all the other fixed points. We asked only about a single memory pattern. We asked about memory pattern number one. We asked, is it a fixed point? And the way to do it was to plug memory pattern number one into this set of equations and see whether they are satisfied. So this is what we will do now. We're going to plug one of the memory patterns, memory pattern number one, into this set of equations as before, and see whether these equations are indeed satisfied. So let's look at the HI. What would be HI if we plug in memory pattern number one? So HI is sum over J of Jij Rj. So, well, we can just write it, but the way that we later did it, and this is a technicality, we took this Jij, we separated Jij into two terms. The first term was mu being equal to 1, and the second term was all the other mu's. And then came the central limit theorem and all these things. But first we separated this into two terms. So we can do the same thing here. So Jij, or Hi, will have two components. One would be the contribution from the first memory pattern, which would be 1 over n, sum over j of pi1 minus f, pj1 minus f, times pj1. This would be the contribution from the first term. Plus, we'll have 1 over n, sum over mu, larger than 1, sum over j of pi mu minus f, pj mu minus f, pj1. Because what we do is we plug a memory pattern as the activity in the network and test whether this is indeed a fixed point. So this is why we did it. Okay. So now again we have two terms. One term we expect to be a beneficial term, or term that contributes to the sustainability of a memory pattern. Another one which we consider as nuisance or noise, which will be detrimental to the memory pattern. So let's look at the first one. Okay, so we can take pi1 minus f outside, pi1 minus f. And here we have 1 over n, sum over j of pj1 minus f times pj1. So we'll have two terms. There will be pj1 squared, which is equal to what? So this will be equal to pj1, because pj1 is 1 or 0. Maybe I will do it. 1 over n, sum over j, pj1. So this comes from the pj1 squared. One over n, sum over j. So here we have pj1 1, and what the second term? F times pj1. So this would be equal 1 minus f, 1 over n, sum over j of pj1. And here we use the fact that pj1 squared is equal to pj1. And we have the second term, 1 over n, sum over mu, sum over j, pi mu minus f, pj mu minus f, pj1. What is 1 over n sum over j of pj1? pj1 is equal to 1 or 0 with a probability s. So this is just this is almost f. Why am I saying almost? Because the memories are stochastic. So this is approximately equal to f. More precisely, there's a distribution here. Because of the central limit theorem, it's normal, or with a mean of f, and variance, which will be on the order of 1 over square root of n. So this will, in the limit of n of large n, this will converge to f, with correction which will be order of 1 over square root of n. So the first term would be equal to f, 1 minus f, pi1 minus f. Okay, what about the second term? So as before, we can write the second term as 1 over n sum over k of zk. This would be the contribution of all these terms. How many elements do we have here? As before, this would be this is I not being equal to j. Let's do it as before. So here we'll have k. We'll have mu going from 2 to p, and j n minus 1 elements here. So the number of elements here is almost n times p. More precisely, it's n minus 1 times p minus 1. So we have almost n times p elements. And what are these elements? So previously, these elements were equal to, well, plus or minus 1, but this is no longer true. So what can we say about zk? What are the possibilities for jk, for zk? Sorry? No, not at all, because, well, it can be 0. If pj1 is equal to 0, then this would be equal to 0. But this cannot be 1, because here you have elements which are either minus f or 1 minus f. So this would be equal to 0. Zk will be equal to 0 with what probability? With probability 1 minus f. So this would be equal to 0 if this is equal to 0. What are the other options? Well, one possibility is that all 3 elements are equal to 1. And then this would be 1, this would be 1 minus f, and this would be 1 minus f. So zk would be 1 minus f squared, and this would happen with probability f cubed. Another possibility is that one of them is 1 and one of them is 0, and this one is 1. And then one will contribute minus f, and the other one will contribute 1 minus f. So here we will have minus f 1 minus f, and what's the probability? What's the probability of this possibility? So we need this should be 1, and one of these should be 1, but not the other. So the first one should be with probability. So this one should be equal to 1. This would happen with probability f. We have two options, one either this one or this one. So we have 2. And one has to be equal to 1, and the other one has to be equal to 0. So this would be 2f squared, 1 minus f. And the fourth possibility is that this one is 0, this one is 0, and this one is 1. And then the contribution would be f squared with probability f times 1 minus f squared. Okay. Are we good? So it's slightly more complicated than it's more complicated than before because we have 4 options now. Previously we only had 2. Okay. So what do we need to compute now? Who said the mean? You said, okay, the mean. Okay. So we have this term, and we need to compute the mean and variance of this term. We need to compute the distribution of this term. We already see that it's a sum of a large number of it's a sum of many stochastic, independent stochastic variables from the same distribution. So we expect it to be normal. It will be normally distributed according to the central limit theorem. So we need to compute the mean and variance in order to fully characterize the distribution. Okay, so let's start with the mean. But the mean is rather easy. Why is it easy? Just look at this term before going and looking at this term. So here we have a product of 3 numbers, and the average of each of these 2 is 0, because pi is 1. P is 1 or 0 is 1 with probability f and 0 otherwise. So the average over over each of these terms is equal to 0, are independent. So we already know that the mean is equal to 0. So we can say that the mean of z is 0. So we are left, and this is why we use the covariance rule. I mean, we expected it. We expected it once we wrote the covariance rule. So next we need to compute the variance. So how are we going to compute the variance? Well, that's easy because we already know the distribution of zk. So each of these will make a different contribution. So what's the contribution of the first term to the variance? 0, because this is an element that is equal to the mean. The second term will contribute 1 minus f squared, so to the power of 4, and this will happen with the probability f cubed. And similarly, we'll have f squared 1 minus f squared, this, with a probability 2 f squared 1 minus f. And finally, this element will contribute f to the power of 4, f squared squared, with probability f times 1 minus f squared. Because it's squared. We compute the variance. And it turns out, and we will not do it because it's straightforward, that this is equal to f cubed 1 minus f squared. So the variance of this distribution is simply equal to f cubed times 1 minus f squared. Okay. What is the next step? I'm sorry? Okay, so what we want to know is whether the sign of hi is congruent with pi, meaning that hi will be positive, or more precisely larger than the threshold for positive memory patterns, and smaller than the threshold for negative, for patterns that are equal to 0. So one way of thinking about it is to look at this term, to consider this term. So there are two components to this term. One component is a component that comes from the first, from mu being equal to 1 in the memory pattern. And you can see that when pi1 is positive, this term is larger than when pi1 is equal to 0. So in principle, we can think about also true that pi1, that this term is positive if pi1 is equal to 1, and is negative if pi1 is equal to 0. So this term is the term that will contribute, that will be beneficial for the fixed point, and this term is a term that is detrimental to this memory pattern. So when we did the Hopfield model previously, what we did was something that we considered as a signal to noise analysis. So what we said was, well, this is a signal, this is a contribution of the first memory pattern, and this is a noise. And in order for a memory pattern to be a fixed point, what we need is that the magnitude of the noise will be smaller than the magnitude of the signal. Now we have a measure for the magnitude of the noise. So we can define this as, we will call it the noise, or the noise squared. And we will define this to be the signal. And we can look at the signal-to-noise ratio. And we expect that if a signal-to-noise ratio is large, then our pattern would be a fixed point, while if the signal-to-noise ratio is small, then it will no longer be a memory pattern. So writing it this way, the signal is equal to f times 1 minus f times pi1 minus f. This is a signal. And the noise is square root of f cubed 1 minus f squared. And what I forgot is the contribution of 1 over n. So this is, the noise is actually is equal to P. Let's do it explicitly. The noise is 1 over n squared. Coming from this, the variance is 1 over noise squared. The variant of this term is 1 over n squared, plus the sum of the variances of these terms, each one having the variance f cubed times 1 minus f squared. And we have n times p such elements. So this would be n times p times f cubed 1 minus f squared, which is equal to p over n, or this alpha that we discussed last time, f cubed 1 minus f squared. So now we can plug this here, and this is what was missing, p over n. This would be equal to pi1 minus f. The f goes with f cubed, leaving 1f, and 1 minus f goes with 1 minus f squared, leaving square root of n over f times 1 over p. The use of n is misleading because here n is noise and here n is number of neurons. So let's give it a different name. Let's call sigma squared the noise. This would be s over sigma, and then we're okay. So what are the implications of this result? F is between 0 and 1, this is correct. So what do we want from this? What do we want from this? Well, we want s over sigma to be larger than 1, or maybe much larger than 1, depending on our tolerance for error. So for this to be true, well, this is not accurate because we want a. Let's go. Let's do it more slowly. So this is a signal to noise, and it can be positive or negative. And eventually, this is the input that we will put in this function. So let's say that we choose t. Let's say that we choose t to be. What should we choose? What would be a reasonable choice of t? What t would you choose? Sorry? 1. Okay, so let's say that, so we are interested now in the sign of hi minus t. Okay. So we have two contributions. We have the mean, and we have this term, and we have this contribution that has zero mean. So let's consider the case that it's really zero. And if we choose, so this term will be between f times 1 minus f times pi minus f. Pi minus f would be, let's choose f to be, I don't know, 0.1. So this would be either 0.9 or minus 0.1. This is much smaller than that. If we subtract 1, then this will always be negative, and then the pattern will never be a fixed point. So choosing 1 is not a good idea. So what's the role of the threshold? Well, the role of the threshold, the role of the threshold is to determine which inputs are to be considered 1 and which inputs are to be considered 0. So again, we can let's say that we choose t, the threshold, to be equal to 0. So if we choose t to be equal to 0, then, well, this could be, and let's say that there is no noise. Then if pi1 is 1, then this would be positive. Then the output would be positive. If this is negative, pi is equal to 0, then this is going to be negative, and then output is going to be 0. So choosing t to be equal to 0 in some sense makes sense because it will work in the absence of noise. The only issue here is that if we choose t to be equal to 0, then if this is 1, then and f is 0.1, then this is equal to 0.9. If this is 0, then this is equal to minus 0.1. So the contribution for positive, for memory patterns that are supposed to be positive, the contribution here would be the magnitude of the signal is 1 minus f. Whereas for if pi 1 is equal to 1, but if pi1 is equal to 0, then this contribution is minus 0.1. So in principle, we can use a threshold to equalize the distance of the two kinds of examples or to move the threshold in order to equalize the distance of these two cases from the threshold. Am I clear? Shall I try and explain it again? Okay, so let's forget about this noise term and just think about this term. So this term has a prefactor and has this component. This component can be, if f is equal, it can be either 1 minus f or minus f. If we take a threshold to be equal to 0, then the quantity here would be up to a factor either minus f or 1 minus f. But you also have this noise term. So you may want to change the threshold so that the probability of mistake for the negative patterns will be equal to the probability of mistake for the positive patterns. So this will allow you to move your dividing boundary between what you will consider as 0 or things that you will consider as 1. Okay? Let's take a break now and finish the calculation after the break.
קראתי פעם באינטרנט, אני ממרתון מרקינג בצד, ולאתרים אמריקאים, כולם אמרו שיש איזה מרכיב אחד, שזה המרכיב חזקאי, שזה משהו מספיק,
ונעים אותו כל הזמן, ולדבר את זה בקייס, זה לא נעים, וגם להרבה יותר זה הרבה יותר מתאים, זה הרבה פחות בריא, זה הרבה פחות
חוץ מזה, אני...
כי אני לא שמה על הסוכר, סילן זה הרבה יותר בריא. הוא ממש לא מבינה מה היה שלך. אתה לא לוקח אותי,
Comment on fait des films comme ça ce soir je mets deux propositions d'exercice en fait.
לא, כאילו, גם מקשיב, אוקיי,
אבל שיפסקי, כאילו
יואו, עשיתי כזה פורים. פורים? ישבנו בדממה.
כאילו, איכשהו בא לי להגיד שכאילו
So actually, we kind of finished the calculation here. If we want the signal, it's not exactly clear what we want from this threshold to be, because if memories are 0 and let's say 0 and 1, or plus or minus 1 with a probability 1/2, then all elements are positive and negative memories are equal in their importance. But if only a small fraction of memories is 1 and the rest are 0, then a mistake of 0 to 1 may be different from a mistake of 1 to 0. So it's not exactly clear what we want for the thresholds. But what is important is that if we want a signal-to-noise ratio, if you want the signal-to-noise ratio to be much larger than 1, what we want is that this term would be much larger than 1. We would like that n over pf would be much larger than 1, or that the p, the number of memory patterns, would be smaller than n over f. So the previous calculation, when we had the full Hopfield model, p was supposed to be smaller than n. Now it's supposed to be smaller than n over f. So there are two things to learn from this exercise, or several things to learn from this exercise. First, we had the Hopfield-like model with 0, 1 rather than -1, 1. That's one new thing about this analysis compared to the previous one. Another thing is that the capacity is order n, same as before. I mean, we can do more elaborate calculations as before, and then we'll have the logarithmic correction. Again, depending how we define capacity, but more generally, the capacity is order n. And in this framework, if memories are sparse, then we can store more of them. From an information perspective, even without using formal information theory, the way to think about it is if the larger f is, or the closer f is to 1/2, the more information there is in each memory pattern. If f is small, then the amount of information in each memory pattern is small. However, we can store more memories. Okay, I'll say it again. The closer f to 1/2, the more informative are the memories. The larger is the entropy or the information content of the memories. And the closer f to 0, the less informative, so the less information there is in the memories. However, the smaller f is, the larger is the capacity of this network. The more memories you can store here. Now, I invite you as an exercise to repeat this analysis with the covariance rule, but going back to the plus and minus 1 neurons. It's a good exercise, and you will find that the memory capacity is still order n, but you don't have the correction of 1 over f. And I leave it to you as an exercise to try and figure out why. So the question is, what is the importance of 1, 0 versus 1, minus 1? I'm not sure that I understand the word importance, not in Hebrew and not in English. What do you mean by importance? Yeah, sure. I will translate. Okay, so now I understand better what you meant by importance. I thought that you meant something else. So I'll first answer about what I thought, because I always enjoy more listening to myself than to anyone else. And only then I will address your question if we will have time and if I remember it. Okay? So one is the issue of importance. So thinking about minus 1 and my importance. Okay, minus 1 neurons doesn't sound right to me. The neurons are active or inactive. Being inactive is not exactly equal to being negative neurons. Okay, so one nice thing here with this example is that we learned that we can extend the hopeful model to neurons that don't have negative activity in them, that have an activation function that it goes from 0 saturation to 1 saturation. So that's one thing that we gained from this analysis. Now, regarding your question of the other importance, right? So you were saying, well, I don't see a difference between this. I don't see a substantial difference between a model plus minus 1 and a model of 0, 1. Why should there be any difference at all? Now, one way of thinking about it is the contribution of is about this term. Thinking about this term. Now, the larger the sparseness of the memories, the larger the number of these of Pj, the larger the probability that Pj1 will be equal to 0. Now, if Pj1 is equal to 0, the contribution, there's 0 contribution to the mean, but there's also 0 contribution to the variance. So, if this is equal to 0, then the activity of this neuron doesn't contribute any noise to the other neurons in the network. While if this would have been minus 1, then there would have been a contribution to the noise. So this is what underlies the difference between the two models. But it's easier to see when you do the math. Okay, a few a few points about this about these results before talking about stability. We saw that the memory capacity is order n, or if we want to ensure that there are no mistakes at all, it's order n over log n. And I told you that as long as the capacity, going back to the original Hopfield model, as long as the capacity is smaller than something like 0.14n, then we have a reasonable number of mistakes, I don't know, 1%, 2%. However, if the number of memory patterns that we embed in this network exceeds 0.14n, something like approximately 0.14n, then everything breaks down. And there are no memories. No memories are there's no retrieval of any memory. And one interesting question is, how much better can we do with other learning rules? So the Hopfield model, you can think about the Hopfield model as a heuristic. There's no guarantee that this particular learning rule is optimal. In fact, it's not optimal. So perhaps we can go up and store order of n square or n cube memory patterns if our learning rule is sufficiently complicated. Is the question clear? Let me try and rephrase it. All the calculations that we made were done assuming that Jij is equal to this particular, that has this particular form. Now, in general, we can think about a learning rule in which Jij is some very complicated function of all the vectors of all the memory patterns. So maybe the optimal Jij, one can envision a Jij that is very different from this Jij. And maybe with this Jij, maybe with this connectivity, one can do much better. Or clearly we expect that we'll be able to do better, but the question is how much better? Maybe the capacity will be n squared, maybe it will be n cubed, maybe it will be e to the n. How much better can we do with this kind of a learning rule? And it turns out, and this is something that you will do indirectly in the Yoram's course when you will talk about the perceptron, it turns out that even if you take the optimal connectivity, still the capacity is order n. More precisely, under certain conditions, if f is equal to 1/2, capacity will be 2n. So you cannot do much better if you take a very complicated learning rule, not this particular plasticity rule. So this plasticity rule, we like it because it's local, because it's incremental, local in the sense that changes between two neurons only depend on the activities of the pre- and postsynaptic neurons. This is what we mean by local. It's incremental in the sense that we can envision a learning rule in which every time we present a new memory pattern and change Jij accordingly. So it's very biological. Here we allow anything. And it turns out that you cannot do much better with a general learning rule. Questions? Okay, no questions. So I want to go back to the original Hopfield model and to talk about the stability. So throughout this course, we talk about fixed points and stability of fixed points. Now, when discussing the Hopfield model, we quickly threw away the beta in the hyperbolic tangent. We replaced hyperbolic tangent with a sine. And we threw away all the dynamics and only talked about the fixed point. Now I want to go back to the dynamics and ask questions about stability. Now, asking questions about stability congruently with a capacity, this is beyond the scope of this course. Calculations are rather hairy and difficult, and some things you cannot do, some things you can. We will go back to the capacity of a network with a small number of memories, but now try to talk about the stability of these fixed points. And again, we will move away from the sign with the sigmoidal function. We will go back to the hyperbolic tangent and not take the limit of, or not necessarily take the limit of beta going to infinity. So this is the plan. So again, our Jij is equal to 1 over n sum over mu pi mu pj mu. This is as before. And Ri dot is equal to minus Ri plus sum over j of Jij Rj. Sorry, G. And G of x is hyperbolic tangent of beta x. And what we did previously was to take beta to infinity, and then G of x became sine of x, but as I said, we are now considering a general case. So the simplest thing to do, if we understand this limit, is what would be the simplest thing? We studied the limit of beta going to infinity. We'll study the limit of beta going to 0. So what will happen to the hyperbolic tangent? Well, it will be equal to 0, but this is not interesting because it doesn't tell you anything about the dependence on x, right? So what would be the first interesting order? So if we Taylor expand hyperbolic tangent, what do we get? Beta x. So beta x is nice because, well, it's easy. That's one reason why it's nice. So in that case, the dynamic equation, or the equations, would be Ri dot are equal to minus Ri plus beta times sum over j, Jij, Rj. So this is nice, right? Because we have a set of dynamic equations. Of linear equations. So what would be the expected behavior of this network? What would be the capacity of this network? All these questions we would like to ask, assuming that beta is small. But we can already say things just by looking at this set of equations. R is equal to 0. What about it? So R being equal to 0 is a fixed point. That's one thing that we can say. What are the other fixed points? What are the other fixed points? What kind of, so looking at this set of equations, we already identified one fixed point, R being equal to 0. So look, my question to you, what will be the other fixed points? Can you identify any other fixed points here? Can you say anything about the other fixed points here? We have a set of linear equations. We were looking for the fixed, sorry? Pattern? So you think that beta time the pattern will be a fixed point. Why? Okay, let's write the fixed point equations in a. Let's write the fixed point equations. So the fixed point equation would be Ri, let's call it Ri star, is equal to beta sum over j, jij, rj star, right? Or using vector notation, R is equal to beta j r. So, okay. This is a set of linear equations. We expect it to have, in general, only a single fixed point. Zero fixed point. We don't expect to see any other fixed points. So clearly, in this limit, if there's a single fixed point, then the network cannot retrieve any memory pattern. So this nonlinearity is in fact very important for the behavior of the network. The nonlinearity is essential for this model to be able to retrieve any memories. And nonlinearity is absolutely essential for this kind of computation. One way of trying to better understand the role of this nonlinearity is to go back and think about the energy function. You remember that because the connectivity is symmetric, then we can use the energy function formulation. So if you remember, energy was equal to, or Lyapunov function more precisely, was equal to minus half sum over ij, jij, ri, rj. There was an external input term that we don't care about at the moment because there's no external input, plus sum over all neurons of a function that we denoted by g of GRI, where g of x was an integral of g to the minus 1 x prime dx prime. Remember, this is what this is. We defined this g when we proved that this is indeed a Lyapunov function. And again, I throw away the external input because there's no external input in this dynamics. So in this case, g of x is equal to hyperbolic tangent of x. And so just plotting it, so we have g of x and x. So this is something that looks like this. And then we have this would be g to the minus 1 of x, and this is minus 1, and this is 1. And I will plot here g of x, so capital G of x, and this is a function that looks something like this. Where the 0 is doesn't matter, it depends on where you define it from. So what is the role of g of x in our case, in this set of equations? So remember that the dynamics, what it does, it's thinking about in the framework of this Lyapunov function, what it does is to reduce the value of E. So the value of E is minimal at 0. So the contribution of this term in the function is to bring all activities of neurons to 0. This is a contribution of this element in the Lyapunov function. Whereas these ones drive neurons to plus or minus, drive the neurons to saturation. So these are elements that drive neurons away from the 0 in the direction, for example, of the memory patterns, whereas this element drives everything to 0. Now, if g of x is approximately beta x, this would be the case when beta goes to 0, then g to the minus 1 of x is equal to what? One over beta of x. It's the inverse function. And then g of x is 1 over 2 beta x squared. So this is a parabola. You have one parabola for each neuron. Now, the smaller beta is, the more dominant this term becomes. So the limit of beta goes to 0. What it does is, what happens is that this term dominates the dynamics. So all neurons go to the minimum determined by this part of the Lyapunov function, which is x being equal to 0. So from this analysis, what we already know is that there is a regime, beta, in which the dynamics is endowed with many fixed points. at least some of them are interesting. These are the memory patterns. Whereas when beta is equal to 0, the dynamics are boring, and all neurons will converge to 0. And thinking about it in the framework of a Lyapunov function, thinking about this E function, this energy function, then we understand that in the limit of beta going to 0, then this term, this integral, where is it? This term dominates, and basically driving all neurons to the minimum of this function, which, because of the shape of this sigmoidal function, is at 0. So somewhere in between of beta being between 0 and infinity, something interesting must happen. So we expect that when beta is very large, behavior will be close to this regime, and when beta is very small, the behavior will be similar to this regime. And somewhere in between, there will be a transition. So what we will do now, we will look for this transition. Questions? Sorry. Okay, let's go back to the dynamic equations. Ri dot is equal to minus Ri plus hyperbolic tangent of beta Hi, or let's use beta times sum over j, Jij, Rj. So eventually we'll be interested in finding what are the values of beta such that this transition occurs between being able to store memories and not being able to store memories. And we will start with the simplest case where Jij is simply equal to 1 over n pi mu, pi1, pj1. So this is the simplest case where we only embed a single memory pattern in the network. And we already know in the limit of beta going to 0 that this will not help, because we will converge to 0. And we already know that in the limit of beta going to infinity, that we will have that we will be able to retrieve, or that pi1 is a fixed point, of the dynamics. Now, in order to study this set of equations, I'm going to define what I call an overlap parameter. And this is somewhat related to these macroscopic variables that Itamar discussed with you, and this I'm going to define this overlap or denote this overlap parameter with mu. And what this overlap parameter tells us is, or denotes, is how similar the pattern of activity in the network is to a particular memory pattern. How similar is it? And it is defined as 1 over n, sum over all neurons in the network, the product of the memory pattern with the pattern of activity. So if all neurons are exactly equal to the memory pattern, then this overlap parameter will be equal to 1. If the pattern of activity in the network is orthogonal to a memory pattern, then the overlap parameter will be equal to 0. So this is an overlap parameter. And the question that I'm going to ask is, what is the dynamics in time of this overlap parameter? So in the case of a single memory pattern, well, there's only a single overlap parameter. But we can still ask this question. So what can we say about M1 dot? Is it clear before continuing with the math? So this overlap, rather than looking at the activity of each and every neuron in the network, I'm asking a macroscopic question about the entire network. And the question that I'm asking is, to what extent is the entire network, or the activity in the entire network, similar to a memory pattern? Will it become more similar or less similar if we start with some overlap with a memory pattern? Okay, so this would be equal to 1 over n, sum over I, pi1 times r1 dot. Which will be equal to 1 over n, sum over I, pi1, and r1 dot is, we can replace it by minus r1 plus, thank you. Thank you. Plus hyperbolic tangent of beta sum over j pi1 pj1, this is jij, 1 over n, sorry, sum over j, 1 over n, jij, and rj. Okay. 1 over n sum over I pi1 times minus ri. What is it? The first term. This is just the overlap, or the product of the vector of memory pattern 1 with a pattern of activity in the network. So this is just the overlap parameter with the minus. So this is equal to minus m1 plus 1 over n sum over I pi1 times hyperbolic tangent of beta 1 over n sum, we can take the pi1 out, pi1 1 over n sum over j of pj1 rj. Right? All I did was to take the pi1 outside this sum. Does this term look familiar to you? This is simply m1, right? Okay, so this is m1. So we have pi1 times hyperbolic tangent of something. Now pi1 is either 1 or minus 1, right? So if this is 1, we can throw it away. If it's minus 1, well, this would be equal to moving it inside the hyperbolic tangent, because minus hyperbolic tangent of x is equal to hyperbolic tangent of minus x. Again, this can be either 1 or minus 1. If it's equal to 1, then it has no effect. We can just put it inside. If it's equal to minus 1, well, we know that minus hyperbolic tangent of x is equal to hyperbolic tangent of minus x. So we can just put it inside. So this is equal to minus m1 plus 1 over n sum over I of hyperbolic tangent